Alright, so my object that's going to be turning at a fixed point at a constant speed will be a Lazy Susan. The tape I have marked at the top with the ruler there is going to show when I look back at the video at what time the Lazy Susan made a complete rotation. So without further ado, let's make it a constant speed. Let's talk about the angular velocity of the Lazy Susan. So, angular velocity is equal to the change in the angle divided by the time. Well, it went 2 pi, which is how long it took to make one complete rotation in 1.05 seconds. When you divide 2 pi divided by 1.05 seconds, you get 1.9 radians per second, and that's angular velocity. Next, we're going to talk about tangential velocity. Tangential velocity is equal to angular velocity times the radius. So, our diameter of our Lazy Susan was 22 inches, so which converted to 0.55 meters radius. So then when you divide that by 2, you get the radius, and radius is equal to 0.275 meters. When you divide the angular velocity, which is 1.9 radians per second times 0.275 meters, it's equal to the tangential velocity is equal to 0.522 meters per second. Next, we have centripetal acceleration. Centripetal acceleration, which is the force that's going into the center, is equal to v squared times r. So it's the velocity, so the tangential velocity squared divided by the radius. So we did the tangential velocity, 0.522 meters per second, squared it, and then we divided by 0.275 meters, which gave us 0.99 meters per second squared for the centripetal acceleration. And finally, we have tangential acceleration. So tangential acceleration formula is equal to radius times alpha, which is the angular acceleration. But our alpha is 0 meters per second squared because the thing was turning at constant speed, so there couldn't have been acceleration because it was going constant. So with that in mind, the tangential acceleration, which is equal to 0.275 meters times 0 meters per second squared for the angular acceleration, you get 0 meters per second squared for the tangential acceleration. So our Lazy Susan here is decreasing speed as we speak. And this is because of the force of friction. Because the force of friction is applying a torque to the Lazy Susan, causing it to slow down and stop as we see here. One way to prevent speed decrease, and not by simply removing the friction, you have to use an external force to keep the Lazy Susan moving at constant speed, such as like a blower.